Hey guys, so today we're going to talk about enzymes and the role they play in metabolism, or building up and breaking down of molecules. The first thing we need to talk about is energy and the laws that govern energy. These are the laws of thermodynamics, and the first law states that energy is neither created nor destroyed, meaning energy has to come from somewhere and it has to go somewhere. It's not just created spontaneously. And the second law of thermodynamics says that disorder tends to increase, especially when we talk about reactions, meaning everything wants to gravitate towards more disorder or more randomness. And another word for disorder is entropy. So you might see those two words and you can use them interchangeably. So sometimes we're going to have to calculate Gibbs free energy, or it might just be known as free energy. And the Gibbs free energy is the amount of energy that's available in a system to do work. And we could calculate that by using a couple different variables. So the first variable, the delta H, stands for the change in enthalpy. And enthalpy is the amount of heat used or released during a reaction. And we can take the difference between that and the product of the temperature, which is going to be an absolute Kelvin, and the change in S, which is change in entropy. And remember, entropy is just disorder. So we could calculate the amount of free energy or the amount of energy available to do work using that formula. And that G, or that delta G, is important because it allows us to determine whether or not a reaction is exergonic or endergonic. Exergonic means that energy is released or exits the system. Endergonic reactions absorb energy, or energy is gained by a system. So if that G value is a positive value, that means that it's an endothermic reaction, meaning that energy was gained. If the delta G is a negative value, that means that it's exothermic, meaning that energy was released. And so these are two graphs to show what exergonic and endergonic reactions look like. So what is metabolism? Well, metabolism is the sum of all the chemical reactions that occur in all of your cells. And there are two types of metabolism. The first is catabolism, which is breaking down materials. And then you have anabolism, which is the building up of materials. And all of metabolism are controlled by enzymes, meaning that these enzymes, or these molecules, are responsible for allowing our body to undergo these metabolic processes at a fast rate. Without enzymes, we would not be able to build and break things down quick enough that our body needed. Here's just a diagram to show what anabolic and catabolism reactions look like. Enzymes work by catalyzing reactions, and that means that they speed reactions up. So if we look at this graph over here on the left, you can see energy, or Gibbs free energy, along your y-axis. If you follow this solid red line, that's the reaction occurring without an enzyme or without a catalyst. So it takes a lot of time and a lot of energy to reach what's called a transition state. And that's a molecule's unstable phase in which we can easily put it together or easily break it apart. If we add a catalyst, we lower that activation energy, meaning it takes less energy and it takes less time to complete a reaction. Here are just a couple of diagrams to show the difference between exergonic and endergonic reactions. You should be able to tell what type of reaction is just by looking at the graph. If the reactants have more energy than the products, like on the left here, that's going to be an exergonic reaction, meaning that energy was lost or released. And on an endergonic reaction graph, if the reactants have less energy and the products have more, that means that energy was gained during that process, meaning that it was an endergonic reaction. So how do enzymes work? Well, first, it's important to note that they exhibit a tertiary structure. They are known as globular proteins because of their shape, or their overall 3D shape. They're substrate specific, meaning that they can only act on one certain type of substrate. For example, lactase can only act on lactose. When we talk about enzymes, there's something called an induced fit model, and what that means is that when a substrate binds to an enzyme's active site, it causes a small conformational change of the enzyme, so that the enzyme actually kind of hugs around the substrate, making it a very good fit so the reaction can occur. All enzymes are reusable, so when they finish one reaction, they're going to go find another substrate that they act on and make another reaction happen. All enzymes are going to end in ASE, so lactase, acetylcholinease, anything that ends in ASE. They can catalyze in both directions. What that means is that if they break a molecule apart, they can also put those two small parts together to make the whole again. So they can speed up those reactions in both directions. We sometimes talk about cofactors and coenzymes. Coenzymes are organic compounds, also known as vitamins, that help control metabolism. And cofactors are inorganic molecules, also known as minerals, to help control metabolism. And all enzymes are affected by pH, temperature, and substrate concentration. pH and temperature, those are two ways that we can denature an enzyme. And then substrate concentration is just a way to maximize how effective our enzymes are. So the more substrate you have, the more active your enzymes are going to be. So we have to be able to regulate enzymes. And our cells actually have different mechanisms to regulate those enzymes. Sometimes we want enzymes turned on, sometimes we want them turned off. So the first regulatory pattern for enzymes is what we call competitive inhibition. So if you kind of break this word apart, competitive means to compete or to fight over, and inhibition means to block. So there are compounds in our cells that mimic the shape of substrates. So for example, there might be a compound in our cells that mimics lactose, which is found in milk. So if we want to shut off that enzyme, lactase, then that compound that looks just like lactose will actually sit in the enzyme's active site. And what that means is that the lactose molecules can't bind to the active site, meaning that enzyme can't be used. That's an example of a reversible inhibition, meaning that once that compound is released, the enzyme can go and do whatever it needs to do. There can be irreversible inhibition, and an example is DIPF, which works with neurotransmitters. But the idea is an irreversible inhibition can never be reversed. It completely shuts down an enzyme. So that's not really common in cells. Because we don't want to get rid of enzymes, we just want to deactivate them for a little bit of time. Non-competitive inhibition is a type of inhibition that's also known as allosteric regulation. What this means is that instead of a compound mimicking a substrate sitting in the active site, there's actually a compound or an allosteric inhibitor that attaches to an area that is not the active site, and then that causes a conformational change, meaning that it causes the enzyme to change shape. So if you look at this diagram over here, you see the active site of the enzyme, but down here is an area where an allosteric inhibitor can bind, causing a change in the enzyme shape, meaning the substrate can no longer fit in there. Another type of regulation that can occur in these pathways is what's called feedback inhibition. And this is when the product of an entire reaction is used as an inhibitor for an earlier enzyme in the same reaction. So it's a built-in checkpoint to regulate how much of a product we're building or how much of a product we're breaking apart. Another type of regulation we can see with enzymes is what's called cooperativity. And this is a way of activating an inactive enzyme. So some enzymes have multiple areas where substrates can bind. So when one substrate binds to one of those active sites, it causes a change that opens up all of the other active sites, like this diagram shows. So that's another type of regulation to control enzyme activity.